Hi, my name is Roberto Orio. I am from the Institute for Microelectronics in Vienna, and this is my talk, Deterministic Spin-Orbit Switching Scheme for an Array of Perpendicular MRAM Cells. The outline of my talk, I will start with a brief introduction about the magnetoresistive RAM. Then I will describe the spin transfer and the spin orbit torque. Then I'll move to the switching of spin orbit torque, and we'll discuss the two-pulse switching scheme which we have proposed, and it's the topic of this work. Then present some simulation results, and finally conclude my talk. STT-MRAM is considered a perfect candidate for future universal memory applications. This table shows some properties of the STT-MRAM in comparison to other memory technologies. And a quick look on this table, we can see that the STT-MRAM is fast, possesses a high endurance, its structure is simple, and more importantly, compatible with CMOS technology in such a way that it can be easily integrated within CMOS circuits. All these features make the STT-MRAM particularly promising for standalone memory applications as well as for embedded applications as a replacement of conventional volatile CMOS-based memories. Embedded STT-MRAM with a density in the order of gigabit and compatible with CMOS technology has already been demonstrated and is currently the state of the art of the MRAM technology. In STT-MRAM, the switching is carried out by passing a current through the MTJ, as shown in this picture on the left, and the spins flowing from bottom to top here. The spins get polarized in the reference layer, and upon entering in the free layer, they are readily aligned with the magnetization here and exert a torque on the magnetization. If the current is high enough, then this can lead to the magnetization reversal of the free layer. In STT-MRAM, the read and write current paths are the same as shown in this figure on the right, and this has eventually poses a problem for these devices where the high write current goes through the MTJ and through this thin tunnel barrier, and these high currents can lead to oxide reliability issues, can generate damage on the tunnel barrier and reduce the general or the overall MRAM endurance. A promising solution for this issue with the STT is based on the spin-orb torque switching. And in this type of memory, spin-orb torque switching MRAM, the magnetic free layer is grown on top of a material with a large spin Hall angle, and by passing the current through this material, a spin current is generated here and flows to the free layer and exerts a torque on the magnetization. So an advantage of the spin-orb torque switching is that the large current required for writing does not flow through the MTJ and through the barrier, so as a result this device shows an excellent endurance, and the spin-orb torque switching is efficient. Even sub-nanosecond switching has been demonstrated, which makes it very promising for application in cache memories. One issue, however, with the spin-orb torque switching is that a magnetic field is needed to guarantee the magnetization reversal of the free layer. When the current is applied and is larger than this current here, which is the critical current for switching, the magnetization is put in the plane of the free layer. However, to complete the magnetization reversal, so in this case to make the magnetization go from Z plus Z direction to minus Z direction, for example, an in-plane magnetic field has to be applied, and the application of this external magnetic field is certainly cumbersome in terms of integration for the cell, and also in terms of scaling, and this is certainly a burden that has to be dealt with. And several field-free schemes have been proposed to avoid using such an external magnetic field. In this slide, I show the field-free switching scheme we have proposed, which is based on application of two pulses to two different orthogonal heavy metal wires. So one first metal wire is here below the free layer. Then there is on top of the free layer a second heavy metal wire partially overlapping it. And to the left here there is an MTJ for the reading operation. And the idea is to control the magnetization reversal by purely electrically by the application of these two current pulses. And although certainly this second heavy metal wire introduces complexity to the structure, the idea is that such a cell could be integrated in some kind of crossbar architecture like shown here, where this second heavy metal wire could be routed over several cells in a row, and which should mitigate the integration problem, although there are certainly technical challenges for realizing such a structure. In order to simulate the spin-orb torque scheme we have proposed before, we have to solve the Landau-Lifshitz-Gilbert equation shown here for the magnetization, and this equation is supplemented with the spin-orb torques, which is given here in this expression below for the first and the second pulse. And in our case, this effective field incorporates the various contributions typically appearing in this equation, which is the exchange interaction, the anisotropy, the demagnetizing, the ampere field, and a stochastic thermal field at 300 Kelvin. Here we show the results for the switching using the two-pulse scheme, considering the configuration, the pulse configuration shown here on the right. And the figure on the left shows the switching of the free layer magnetization, which is initially pointing to the plus Z direction and then goes to the minus Z direction. In this case, the currents are set so that the current density is larger than the critical value, and later we will discuss cases with the second current amplitudes lower than the critical value. But what we can observe on this picture is that the switching is deterministic across a wide variation of the second pulse width, as we can see here, and also that the switching times are practically constant, so they change slightly with for a wide range of second pulse width variations. One goal we had for this work was to reduce the applied current, in particular the second current, and we verified that indeed the switching current can be reduced provided that the pulse width is eventually adjusted to guarantee deterministic switching, as this picture here on the left shows. But even if we have a short pulse, set a short pulse like 200 picoseconds, we still observe that the current can be significantly reduced without affecting so much the performance of the cell. So here we could reduce the current from about 130 microamps to 60 microamps, so about 50%, without affecting so much the switching dynamics, and still guaranteeing deterministic switching. One of the main consequences, an important consequence of this current reduction, is that we could observe a significant reduction in the riding power, in our case of about 40%, as shown in this table. The previous results were based on a nominal set of parameters. Now we consider the effect of parameter variability, in this case plus minus 5% of variation in the saturation ionization and the perpendicular anisotropy constant. And we found out that the current of the first pulse, here given by I1, has to be adjusted, and in this case it means that the current, this first pulse current, has to be increased to account for this variation either of the magnetization saturation or the anisotropy energy. So this increase was about 20% to guarantee the switching, deterministic switching of all cells across this variability space. And the explanation for such a need of increase of the current is because as the saturation ionization or the anisotropy constant changes, this leads to a change in the critical current density for SOT switching, and so the first pulse current has also to be increased to account for this critical current increase. We further extended this variability analysis and considered the extreme cases of variation of MS and K, basically taking the four corners of the plus minus 5%, and checked the impact of such variations on the current amplitude of the second pulse here in the left and on the pulse duration here in the right figure. For the pulse duration, a minimum of 150 picoseconds was observed, and to guarantee deterministic switching of all cells within this variation, and which is rather short, and it's consistent with typical values of 200 picoseconds that we have used previously. So this is not really an issue. On the other hand, for the current, we observed that yes, some cells could eventually be switched with quite a low current pulse, so in the order of 40 microamps, also consistent with some results for the nominal parameters. Nevertheless, in order to guarantee really switching of all cells across the variation space of this saturation ionization and anisotropy constant, a current of about 60 microamps is required. It is important to note, though, that this current is still quite low and lower than the critical current for these cells, which is about 120 microamps. So this is an important aspect, as I will discuss in the next slide. This feature of low second current is important because if we consider an array of cells routed with a single NM2 wire, as shown here in this schematic, the second current has to be low enough so it does not lead to unintended switching of an unselected cell. So it has to be low, not to affect the magnetization of neighboring cells except that cell that was previously selected with the first pulse. We verified this condition by applying only the second current pulse in a cell, and we could check that indeed the magnetization is very slightly disturbed, as shown by this figure on the left. Here we show the magnetization, Z component of the magnetization very slightly affected. And then we further increased the current also above the critical current here, so 120 microamps and 160 microamps, so going above the critical current density. And even with such currents, we still could observe that the switching was not happening due to the second pulse only. And this condition is provided because the second heavy metal wire is only partially overlapping with the free layer, so although it affects locally the magnetization here under the free layer, it does not lead to a general switching of the free layer. So to sum up my talk, we demonstrated via numerical simulations the magnetic field free switching of a perpendicular magnetized free layer by spin orb torque. The magnetic field required for completing the switching is created dynamically, and this is using the two current pulse approach we have discussed. The switching remains fast and deterministic for a wide range of pulse parameters, and we observed that the switching current can be lowered, so the writing power is significantly reduced without affecting the switching performance. Thank you very much.